Yeah. Cute, cute. Where'd you see this now? He sent it to you. Alright, let's continue. Specific heat capacity. You got this, Sean?
Yes.
Sean?
Wow.
Sean? Did you write this down? You did?
No.
Yeah. Specific heat capacity. This word is a new word for you? Yeah, what does it mean, Monica? Go for it.
Design one.
Unique.
Specifically to what?
Unique to that thing.
Yeah.
It's hard to explain.
Just that thing.
They're not doing a good job.
I'm just seeing the hand movement.
Not working for them. In fact, the word specific in this title is a little bit redundant. By redundant, I mean it's not a necessary word. Example, like if I said today we will study cold ice cream. Well, I don't need to say cold because ice cream is cold. So here the specific in specific heat capacity, I think it's a little bit redundant. It just means the heat ability of one thing. But of course it's always going to be one thing. Because we understand that everything has different behaviours. You know. So I feel it's a little bit redundant. Anyway, it's heat capacity is what we're going to study now. Continue? Yep. So, why does metal feel colder than plastic?
I know this.
Go for it.
Because metal conduct heat.
It's because metal can conduct heat. So it's quite easy for the heat to flow from your hand to the metal. Also, if you put metal and plastic on a heater, which will get hot first? The metal. So we understand that although we might put the same heat energy into things, we understand the temperature increase will be different. So if I put some heat into my coffee or some heat into my pen, the pen will probably get hot before the coffee, because water is quite difficult to make hot. In fact, water is one of the most difficult things to make hot. You require a lot of energy to warm water. Yeah? But you don't need much energy to warm some metal. It's quite easy to warm metal. So we need to talk more about this. We need to talk about conductors and things like that. Some materials warm up faster than others. Why is this? Well, different materials have different capabilities when it comes to absorbing heat. So different materials are able to take heat in different ways, at different speeds nearly. So let's be more precise here. When I say the specific heat capacity of a material, what I mean is how much energy I need to increase 1 unit mass by 1 unit of temperature. So for example, just before you write that down, for example, if I have water, the specific heat capacity, which we use the letter C for, that's how much energy I have to put in so that it is 1 Celsius warmer and it was 1 kilogram to begin with. You understand? In fact, for water it's something like this, 4,000 joules about. To make 1 litre 1 degree warmer, you need nearly over 4,000 joules. So, it's the amount of energy required to raise 1 unit mass by a unit of temperature. This is the heat capacity. You can use kilograms and Celsius and Kelvin, or you can use grams and Celsius and Kelvin. It's fine. Okay, can you write this definition down? It's a common definition for the materials chapter in the exam. In fact, I should tell you, for this chapter, the whole chapter of materials in the exam, there are two definitions they love to ask in the final exam. This is one of the definitions, heat capacity.
Yeah.
You might even know it. We haven't done it yet, but you might have a guess at what it could be if you've done this before. Huh?
Latent heat.
Yeah,
What?
latent heat. We haven't done it yet. Can you write beside this definition one of two important exam definitions for this chapter?
Can we use 1 kg?
Ah, yeah, of course. Yeah. You could even use 1 kg and 1 Kelvin would be good.
Kelvin, not degrees Celsius.
It's fine, but it's a little bit better to be using Kelvins. Yeah?
What about fire?
What about it?
Like, do we have a measurement of until what temperature you will cause fire?
No, because fire is a chemical reaction, isn't it? Like,
But it's a matter when you heat up until a specific temperature, it burns with fire.
yeah, it combusts, I suppose. But it's usually more that when it's hot, it's just the conditions are better for the fire to start, really. Like a forest fire starts not really because it's hot, but because it's so hot and dry, it means if somebody dropped a glass bottle, that the heat from the glass could burn a little hole in a leaf. And because it's so dry, there's no moisture, then this can very quickly spread. So it's not because the forest got hot that the fire started, it just made the conditions favourable for the fire to start and to spread. I think this is a more helpful way to think about it. What will happen is if you heat something up, it will become a liquid and then become a gas. But of course, to heat it up, you have to put it in a fire. So you're not really making, you're not turning it into fire. You're putting it in a fire. Okay, continue. Let's look at the units. So what would the units here be for specific heat capacity? What would the units be, do you think? Joules, yes, go on, Jerry. Oh, come on, it started right. Go on, joules, yeah. Ah.
Per kilogram.
No. Try again, joules.
Per kilogram.
Yeah, per kilogram Kelvin. So the unit here is joules per kilogram Kelvin. It's how many joules for each kilogram in Kelvin you need. That's the unit.
Yeah, I mean, it has
Huh?
joule multiplied.
Yeah, it's not joule multiplied kilogram. I knew that's what you meant. That's why I said it's not right. Got that? Okay. Joule per kilogram Kelvin, or joule per kilogram Celsius, or joule per gram Celsius. Yeah. Okay. So the energy, if we think about the units, then we can get this formula. The energy you need to increase m kilograms by delta theta, I think Bruce knows this formula. You told me this formula earlier, Bruce. Q equals mc delta theta. The energy you need is the mass you have multiplied the capacity of the mass multiply how much temperature increase you want, where C is for the material. Yep. Got that?
No.
Right. Have you seen this formula before?
No.
No.
Funny man, Bruce.
What about the other thing? Like,
What about
straight to the surrounding. Like, we supply the same heat energy to both same thing, but they have different specificity of capacity. So what about the astral one? The heat.
we haven't done any examples yet. I'm going to do examples where we're heating two things at once. Don't you worry. I know what I'm doing. I'm doing this now for 10 years. Don't you worry. Under control. Yeah, I know. Unbelievable, huh? You're thinking, what have I done so wrong in my life to be doing this for 10 years? I don't think
10
so.
years ago,
10 years ago, he was 7.
I'm in.
only my 7 years old.
When I was 7, you are not.
Good singing.
What about you, Christy?
I was in my first grade. I'm
I was 15.
Oh, okay.
So difficult.
No!
Isn't it crazy?
No!
Even he goes to the
No.
elementary school, the primary
Too
school.
warm.
I also
Yes,
did
sure.
it.
Jeremy's the baby of the class.
Yes.
But you know, this is a one. Hey.
Who is the eldest?
Sean.
Is Sean the
Probably.
eldest? Why?
God.
Why probably?
Just guessing. Yeah.
I can't really tell your ages from looking at you necessarily. Who is the eldest?
Sean.
Who looks the oldest?
You.
Me.
Obviously, I'm the eldest. Obviously. How old are you, Sean?
Guess.
Guess is the age.
39.
Year 30.
24.
No.
No.
Too big or too small?
Too small.
Oh. 27.
Yes.
I'm young.
Yes?
Yeah.
Excellent.
Wow, 10 years later. I'm 30.
Oh yeah.
30.
10 years later? Oh my
Yeah,
god.
future Jerry.
Wow.
Past Jerry, future Jerry. Yes, yeah. Good.
I'm not that old.
Yeah, I know.
Yeah.
You're how old?
Yes.
Guess is the age.
20.
Thank you.
No. 12.
Go. 16.
I'm 18.
Yeah. Okay. You need ID when you go buying your drinks. They believe you. Good for you.
Yes.
Okay. Next now. So now we need a table of different heat capacities. Okay. So the first one we'll start with is water.
Water.
So like I said, you need 4,000 joules to make 1 kilogram 1 degree warmer. That's a lot. 1 degree is not much, but you need 4,000 joules. That's a lot. Let's compare this with other materials. Ice, believe it or not, even though it's water, it actually only needs half as much energy to get warm. And gas, steam, again about half. Right, let's look at other materials though. So let's take something like a metal, copper. Look at the difference between copper and water. For the same amount of energy, you could increase the temperature of copper 10 times.
Yes.
More than 10 times. More than 10 times. For the same amount of energy, 4,000 joules about. Because copper is a conductor. Milk.
Milk.
I decided to look up what milk was because I was wondering what milk was. Milk is not as much as water.
Milk.
What? You all know what milk is. Why are you being stupid? You know what milk is. What's so surprising that I used milk as an example?
Yes.
Milk considered as a bit oil, like oil.
Well, I guess it might behave like oil, but it's... I mean, do you pour oil on your cereal? Right, so milk is about 3,000 joules. Okay, next. Alcohol, about 2,300. And we'll also do lead. Do you know lead?
No.
PB?
No.
The farm.
Oh, yes, PBS.
I hope so. Now look at how small lead is. Only 129 joules, and you can increase the temperature. Not much. In other words, it's very easy to warm lead up. Very easy. Okay. And finally, air. Now, I don't know if this is bigger or smaller than what you thought, but it's actually kind of large. You need 1,000 joules to warm up a kilogram of air, which is about a meter cubed of air. Yeah. You'll need to write these down, please. So these are all the important materials.
All of them. I just write like some of them. What's your okay?
Let's see, I said write all of them and you're confused.
Because they will be given in the question, right?
No, for the questions I'm going to... No, they'll be given in the exam, but not the question I'm going to give you.
Oh, okay.
Just write them down. Just write them down, Lee. Just write them down.
Sorry.
In fact, it's very important that water is 4,181. It means water... Yes?
Yes, I know that one.
Go on, Sean.
I know, this is which
Hang on. Sean's going to tell us. Then you
I
can
know
tell us.
this in Chinese, but not in English. Sorry.
Try, Sean, try. Jerry, what were you going to say?
I mean, different spaceship use water to observe the energy from oil or H2.
Use water in the ship.
Use water in pour like their spaceship.
Yeah.
Flash it, and then fire.
Yeah.
The like fire.
Yeah.
Use water to reduce that of sound energy.
Yeah, you can use water to reduce the energy because water can take a lot of energy. And that's what I was about to say. Water is important that it can take a lot of energy. It's important for life because we're all mostly made of just water. And this means we actually have a lot of heat energy stored in us. Yes? You understand what I'm saying? It is difficult to make us warmer or colder because it would require a lot of heat energy to go in or to come out. So this means our temperature is quite stable. An important feature for life because it's difficult for life to succeed if it's so easy for it to become cold and die. You know? Also, you know, the fact that our planet is mostly water and water can take so much energy, it means the ocean acts as a sort of way to balance the energy. When it's too hot, the energy is stored in the water, and then when it comes to winter, the energy then is released. So believe it or not, the ocean helps keep us warmer in winter and colder in summer.
Yes.
And you notice this when you go to the beach, because the beach will be a little bit colder than in the summer from the water. Now, this is important because if there was no water, it would also mean in the summer it gets very, very hot,
Yes.
and in the winter it gets very, very cold. And again, this is difficult. This sort of up-down is difficult for life.
Yes.
Yeah. Yeah.
No.
Yeah, the beach. Now, if you go to the coast, it'll be warmer than inland. Now, not that I didn't say it'd be warm. It'll be warmer. And anyways, we're already near the coast, so we're not going to notice much difference. You know, we're only like, 2-3 kilometres from the coast, so we're not going to notice much of a difference if we go an extra 2 kilometres.
But it's very windy out there.
Yeah, well obviously if there's a cold wind blowing in, you're doing work to take heat away, you know. But usually the ocean will sort of act as a counterbalance.
Teacher,
Yeah.
is there any difference between seawater and
Yeah, there is actually I can't remember what the difference is exactly, but salt water will have a different heat capacity.
Oh, different.
Yeah, I believe it will be less,
Less.
or will it be more?
More.
Less.
That's
Seawater is less than
It's
fresh.
less.
Yeah, yes.
Yeah.
Less.
I think
because
it's
seawater has
Salt.
metal.
Yeah.
So it's less.
I think it'll be less, but I have to check it. Okay, continue. Right, why do different materials have different heat capacities? Like, why is milk different to copper, different to water? Why? Any ideas?
What do materials have different nature?
Yeah. Wow.
So that's a different material.
Yes.
To differentiate them,
Different.
it's like an ID.
It's the main.
What's your ID number?
Different
4181.
structure.
Oh, water. Okay.
Different chemical structure might be the material.
What?
正子层是什么？我不知道。
Hey.
Atom.
Huh?
Atom.
Closer, yeah, not bad idea. Sean, what are you saying?
Because the different metals have a different.
What is 正子层？Energy level.
Possibly. Well, let me say. Let me say. Let me say.
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 It's complicated.
What?
And we might look at it later. It's actually pretty complicated why different materials would have different heat capacities. It depends on many things. It depends on the atoms. It depends on the spacing. It depends on the energy levels. It depends on the chemical compounds. It depends on many, many different things. Okay. How long would it take to boil water to make a cup of tea? If we use a 1 kilowatt, a small 1 kilowatt electric kettle. Okay, let's do this one together. So, I want to make a cup of tea. And I have an electric kettle. It's a small one, okay? It's one of those little travel ones, a small one. It can hold... How much do you think it can hold? You know the small ones you see in the hotel, maybe? How much?
500 milliliters.
I think you could maybe do a litre. Okay? And it's 1 kilowatt is the power.
Yes.
How long will it take to make the tea?
1
Okay.
minute.
Well, let's calculate it, okay? So what's the formula for power?
P 等于
Work
Work over T.
work over time, yeah. So time is work over power,
Power.
which is work over 1000.
Yes.
What is the work being done?
Heat up.
Yeah, the work being done is the heat is being given to the water. And we have a formula for heat energy, MC delta theta. Okay, well, what's the M?
1
1
kg. And the C is 4180. And what's the delta theta, the change in the temperature?
75.
I think it's probably more than
100
75.
minus 25.
No. What temperature will we say the water is at the start when you put the cold water in?
25.
Hang on. How long have you been in Ireland? When you turn on the cold tap, does this feel like 25? Come on.
No.
Not serious.
No, it's odd.
Yeah, exactly. Come on.
Cause it. 18. 18.
No, it's 16. I'm not sure what.
I would say, I'd say 10 is probably what it is. And what are we trying to get it to?
100.
100. So what's the change?
90.
90. Okay. Right, let's calculate this. This will be about
10,000.
about 6 minutes.
6
Minutes.
It's
minutes.
not
No.
How many seconds? What is it?
376.
Okay, well 300 is 5, so 6 minutes and 16 seconds. Yeah. So that's how long it would take to make the tea. It would take 6 minutes. Now, if you use a kettle at home, the kettles at home in your home are probably 2 kilowatts. So what would happen to the time?
3 minutes.
It'd be 3 minutes 8 seconds. Yeah. Yeah. Continue.
Oh, no.
This is our first example. Yeah.
One liter water is 1 kg.
Yes. I think I must have said this 100 times now. Okay, next one. Right. I'll let you do this one. A 100 gram block of ice is at -10. How much energy do you need to warm it to -1? Okay, you can calculate this pretty quick, I think, if you use the table. So we're going from -10 to -1. What's the delta theta?
Minus
9 plus 9. It's an increase.
9.
What's the m? 0.1.
1.1.
0.1. And the c is something like 2000?
2110.
Okay, tell me what the energy needed is, please. What's the Q?
1899.
1899?
1899.
Great, 1899. Okay,
Yes.
good job.
Yes.
Next one. Congratulations on multiplying. Good job. Right, continue. Yeah. Okay. An electric heater of 3 kilowatts is used to heat a room that is 10 by 10 by 5. And the room is 10, and we want its temperature to be 20.
Yes.
How long would it take for the room to reach this temperature? Okay, let's draw this. So let's do this together. We have a room, let's see, it's like this. Come on, roughly. 10,
5.
10 this, yeah, we'll say 10, 10 this way, and 5 this way.
Yes.
Okay, and this is air. And in the question I said the density of air is about 1 kilogram per meter cubed. And there's a heater, and the heater is 3 kilowatts,
Yes.
and the temperature is now 10, and we want it to become 20. So, how long do we need the heater on to do this? Let's calculate this. So, power equals work over time. Yeah. So time is work over power. which is delta Q over power, which is MC delta theta over power. But of course the problem is we don't know the M, do we?
Yes.
But we know density is M over V.
Yes.
So that means the T will be density, volume, heat capacity, change in temperature over power. So that will be 1/500 1 10 3000. So this is 5,000 over. It's air. Oh, no, sorry.
1012.
Thank you. 1012, and then
10.
over 3,000.
3,000.
Okay. So let me see. Yeah, what would that be? That would be 5,000 times 1,000 is 5 million, is it? Over 3,000.
You can do it.
Yes, you can do it.
Do it.
Fine.
Go.
Leave me. 5 over 3, 1.67 times 1,000, 1,600.
Somebody.
What is it?
28 minutes.
Okay. Thank you.
Teacher,
Yes.
how do we usually calculate the temperature in the room?
Thermometer on the wall. Okay, continue?
Yes.
Yep. Right. Next.
Because I try very hard.
A physics student is making a latte. He mixes 200 grams of hot milk at 27 Celsius to 50 grams of hot coffee at 80 Celsius. What is the final temperature of the delicious, warm, steamy latte? Okay. So, hot milk, hot coffee, mix it together. What's the temperature? So this is what we were looking at, or you were mentioning earlier, like how do we deal with more than one thing? So this is a good example. So let's just draw what we have, okay? So the story starts off with, he has 200 grams of milk,
Yes.
and then he has 50 grams of espresso. The milk's temperature is 27, and this of course is hotter. 80. Yeah. What's the heat capacity of the milk? 2850. Now, do we know the heat capacity of the coffee?
No.
No, we don't. But let's guess at what it is. I mean, what's the closest? Well, I mean, in the table I gave you, what's the closest thing to coffee in the table? I think the water is the closest thing. I mean, when you think about it, the coffee is just hot water with some powder in it. So it's going to be pretty close. I think it'll probably be less though, but it'll be roughly this.
Close to water.
Huh?
One coffee is close to water, not to milk.
No, because milk has lots of fat in it. Could be close to this. No, it might be. Milk is very different to water and coffee, because milk is very creamy and fat.
We can, yeah.
Yeah. Anyways, I think the coffee is most like water.
Okay.
I mean, think about when you make coffee. Do you put the coffee powder in hot milk or hot water? Or hot alcohol too?
Hot milk.
Yeah.
Milk.
Yeah, no, but a latte is milk after you add the coffee in. So first you make the coffee,
Yes.
and then you all drink lattes, don't you?
Yes,
Yeah.
yes,
So first you make the coffee. How do you make the coffee? With hot water and coffee beans. Then you put it in the milk.
Yeah.
Come on. Oh, sorry. Some of you drink frappuccino, so it's a different principle. Yeah.
Yeah.
81.
Okay. 4181. Thank you. Right. Okay. And now these are added together and mixed.
Yeah.
Yeah. So there's the coffee, and there's the milk. Now, in our mind, we all know it's mixed together, but it's easier to imagine that they're still separate in the cup. But of course, in real life, they're mixed together. All right. Let's calculate this. I don't know the temperature. I want the temperature. I know that at least they'll be the same temperature.
Yes.
Okay. Let's keep track of what's happening here. What will be the final temperature? We don't know, but we do know it'll be between 27 and 80. We know that. It can't be more than 80, and it can't be less than 27.
Why?
Well, nothing was less than 27 at the beginning, and nothing was more than 80 at the beginning. So when you mix them, it can't be past that. You know, it can't be colder than the coldest part that was put into it, and it can't be hotter than the hottest part that was put into it. If it was hotter than the hottest thing you put into it, then you've just made energy. Yeah? What? Trust me on this.
Yes.
Okay.
Absolutely.
Is this gaining or losing energy, the milk?
Gaining.
It will gain energy. Will this gain or lose energy? Lose energy. Okay? Come on, guys. Leave Bruce alone. Right. Now, the energy the milk gains, that must equal the energy that the coffee or the water it lost, yeah. Because it's balanced. Yeah.
Yes.
Okay, so let's calculate this. This will be M C. Now, what is the change in the temperature? It went from a 27 to an X. So its change was X minus 27. And here this will be M
Yes.
C, and it went from 80 down to X.
80 minus 5.
80 minutes.
80 minus X. Very good, very good. So we need to solve this. Yeah, now we'll have to multiply this out. Monica, sorry, can you give me what happens when you multiply these two together?
570.
What is it? 570.
570.
Exact?
570.
Nice. 570x minus 570 times 27 equals, and then what's this one? 2.
209.
Yeah.
0.05.
And is that with or without the 80? Without the 80. So then it's still 80 minus and that x. Okay. So that would be 570x plus 209.05x equals 209.0580 plus 570 by 27. So I get x equals 209.05. Sean, can you type this in? Times 80 plus 570 over 27, times 27 over 570 plus 209.05. If it's opposite day now, does that mean you'll be less annoying and helpful today?
41.
Huh?
41.
41. And this feels like the right answer, doesn't it? You have your hot milk at what
We
temperature?
have to plus the 27, right?
No?
Oh, this is not a change.
No, this is not the change, this is the X. 41 Celsius. This seems like the right answer. You know, you have your very hot coffee with your hot milk, you mix it together and you get 41 Celsius latte. You can test it. Yep. In real life it will be less than this because heat leaves the coffee cup.
Yeah.
In real life. Yeah. So right now this is probably at room temperature. Yeah. Okay. Continue. Let me hand out these questions here. You can take one and pass it along, please.
Wow.
What?
What's this?
Usually the back.
Read the question.
That's a picture.
Yeah, read the question. It explains the picture.
Sure, guys.
Look at the top.
Two.
My computer is having a problem right now. Just a second. It's running low on power.
Monkey.
This was the question. And this is the answer. I need to stop this.